Last time we did chapter number 1, which was given the name Introduction, but actually it was not introduction, it was the baseline, it was the base concepts based on which everything else will be built in the whole course. Today we are going to start from the first mode of heat transfer, which is conduction. Now basically conduction is divided into 4 chapters here. Okay. Chapter number 2, 3, 4, 5. All these 4 chapters are only about conduction. So the thing is that chapter number 2 itself is an introduction to conduction. Itself is an introduction to conduction, which will develop the baseline to be used in chapter 3, 4, and 5. So we are going to develop the conduction main heat diffusion equation in this chapter. And that equation is the baseline for chapter number 3, 4, and 5. Okay. So chapter number 3 is basically one-dimensional steady state conduction. Where I discussed that in the previous lecture. What does one-dimensional means? Okay. So it's one-dimensional steady state conduction. Then chapter number 4 is 2 or 3-dimensional steady state conduction. And chapter number 5 is unsteady or transient conduction. Okay. So anyways, we are going to go and study it in detail. So let's move ahead. For conduction, we already studied that it follows Fourier's law. Okay. And we studied that in chapter number 1, that Fourier's law is Q is equals to negative Ka dt by dx, or you can say Ka delta t by delta x. Okay. This is the Fourier's law. Okay. And you know about all these terminologies. K is a material property. That means if you change the material, K will change. If the material is same under the same conditions, the K value will not change. And A is the area the area perpendicular to the direction of heat flow. So if heat is flowing in this direction, so the area is perpendicular to that. Okay, across which the heat is flowing. So the area is a very critical thing here. Most of the time you have to consider that what area you have to use based upon what is the direction of flow of heat. Then delta T is the temperature difference across which heat is being transferred. Delta X is the distance. Okay. We define a surface known as isothermal surface. So what's this isothermal surface? This isothermal surface is basically the area across which heat is being flown. Okay. So whenever the heat is flowing, so the perpendicular area, we consider that it has the same temperature in that area and the heat is flowing across it. So that surface becomes isothermal surface. Okay, let's move ahead. Now in the vector format, we can write the heat conduction equation as negative K del T. Okay. If you have studied vector algebra, you can understand that very well. And del in the vector algebra, it refers to change in x, y, z coordinates all along. So it's not necessary that the transfer or the change in temperature is along x-axis only. Maybe the change in temperature is along y-axis as well as along z-axis. Okay, yeah, if it is one-dimensional, then it is like this. We're going to have 3 dimensions, this possibility. Okay. So since we are developing the generalized equation, so we have to work in the 3 dimensions. Okay. So it's negative K del T, or you can write here negative K dou T by dou X, dou T by dou Y, dou T by dou Z. You understand the difference between D and dou? When we write D, when we write dou? Partial. This is partial, this is total. So if something is varying with only one thing, so for example, delta dt is varying with x only, just variation of t with x only. So if this something is varying with one thing only, then we write d. That's total. Okay, if it is varying with more than one thing, also varying with x, also varying with y, also varying with z, then we have to write dawa. Okay, well, that's why since t here is varying with x, y, and z, so we write here dawa t by dawa x, dawa t by dawa y, dawa t by dawa z. Or in a more generalized form, we can write it by dawa t by dawa n, where n could be x, y, z, depends upon. Okay, that's the vector format. Now K, thermal conductivity, is a transport property, provides an indication of the rate at which energy is transferred by the diffusion process. So physically K means what? Physically K is a transport property. It is transporting what thing? It's transporting energy, transporting of heat. Okay, so I have a material which has two different temperatures, so the heat will be transferred from the high to the low temperature from the material. So that's the property of the material, how quickly it can transfer the heat. So it is transporting energy, it is transporting heat. So K is basically a material property, but what kind of material property? It's a transport property. Okay, K, material ability to transport heat. Okay. Whenever you have a transport property, it has okay. Now there is another definition, or there is another concept. For most of the materials, the transport property is independent of direction. So if I have a body, let's say suppose I have this made of iron or copper, so the transport of heat from this end to this end will be the same as from this end to this end, or whatever. If the temperature differences are same, then the transport of heat would be same because the material is same. But sometimes transport properties also vary with direction. So there might be some material for which it has good transport property in one direction, but not a very good transport property of heat in the other direction. Okay. Now this thing is hard to visualize in reality. Okay. But instead of, if you forget the heat and mass transfer, for instance, okay, let me explain it to you with a paper. Okay, paper has a property that it can bind to itself. It can maintain its. It's hard to tear the paper if I push it like this, but it's very easy to tear the paper if I do like this. Okay. Change the direction, the paper resistance is different in different directions. This is just an example that I gave you, that it's the same paper, but if I try to tear the paper like this, it's very hard. But with the same force, if I tear it like this, if I just change the direction of force, it's very easy. Okay? So this happens. There are some material which has different transport properties in one direction and different which are stronger in one direction and weaker in the other direction. The same is the case with the heat as well. Sometimes some materials have good heat transport capability in one direction, but not very good in the other direction. Okay. So anyways, but most of the materials that we are going to deal are the ones which have same transport properties in all directions. Okay, which has same transport properties in all directions, and those materials are known as isotropic material. So K is the thermal diffusivity, which is the transport of heat. So for the isotropic material, Kx, Ky, and Kz are all same. So transport property in x direction will be the same as transport property in y direction, will be the same as transport property in z direction. That means it is independent of direction. Whatever be the direction, it will be same. Okay. So that's the concept of isotropic material. Do you understand the concept of isotropic material? Okay. So for isotropic material, Ky, Kx, Ky, Kz all are equals to K, because all are same. Okay. In general, the thermal conductivity of a solid is greater than that of a liquid, which is greater than that of a gas. It's a transport property, but you have to understand how does this transport is occurring. It's because the molecules collide with each other and transport energy. In case of solids, the molecules are too compact that the transport is very quick, because this transport is by diffusion. Okay? Because the molecules are so compact and close, so there will be more and more collisions and more heat transfer. In case of liquid, molecules can move around. So transport because of the diffusion is comparatively less than the case of the solids. In case of gases, the molecules move around and they are too far away than even in liquid. So the K value, so there is diffusion property within the solid, there is diffusion property within the liquid, there is diffusion property within the gas. But the diffusion, heat diffusion within the solids is very high compared to that of liquid, and liquid is higher than that of gas. And you do understand now why. Okay? Because the intermolecular spacing is much larger and the molecular motion is more random as compared to the case of a compact lattice structure in solids. Okay? So I can ask you a short question about why. Why do we have K value of solid greater than that of K value of liquid, which is greater than that of K value of gas? Is there any question you need to ask? This is just a diagram which will give you a sense of the K values, that the thermal conductivity values for the gases is very, very less, normally in the range of 0.01 to 0.1. In the case of the liquids, it's normally a bit higher, from 0.1 to 10. Then in the case of the, then we have the non-metallic solids, then we have the alloys, then we have the pure metals. Pure metals have the highest conductivity, okay, and which is in the range of 100 to 1000. Okay. So we have different ranges. Anyways, this graph is not intended to, you don't intend to learn the graph, we just give you a sense of the values. Okay. Which one?
If the K is high now, that means the heat is moving
fast, very quickly. Okay. So I have a very long rod, I heat it on one end. If the K is high, the other end will have the effect very quickly. If the K is very low, then the other end will not have that quick effect. Might be the effect will come, but after a very long time. Okay. So we have thermophysical properties that includes two distinct categories, transport and thermodynamic properties. Now transport properties includes diffusion rate coefficients such as the thermal conductivity you already studied, and kinematic viscosity. Kinematic viscosity you studied in fluid dynamics or fluid mechanics, whatever. So it's also a transport property, but it's a transport property of the disturbance of motion within the body. Okay. So the best example is if I have, let's say, a bowl of water. This is a bowl of water, you're looking from the top, okay, and the water is all 25 degrees centigrade, and I have a ball, small ball or anything, a stone, 100 degrees centigrade, and I drop it in the center. Now when I drop it in the center 100 degrees centigrade stone, now there is disturbance in the system. That there are two kind of disturbance here. One disturbance is that the whole thing was 25 degree and you drop something of 100 degree. So there will be a transport of heat. Second disturbance is that because you throw the stone into it, so the body itself is disturbed, and the disturbance will be propagated as wave. So you will see a wave propagating. Wave will flow. Okay. Now the propagation of wave here is depends upon the diffusion of momentum. That's kinematic viscosity. So if kinematic viscosity is higher, the wave will be very quickly moving. If the kinematic viscosity is low, then the wave will move very slow. Okay? And similarly for the case of diffusion, if the thermal conductivity or thermal diffusion is high, then then the flow of heat will be very quick from center to the out. If it is low, then the flow of heat will be slow. Is it clear? So these are the transport properties: kinematic viscosity and thermal conductivity. Then we have thermodynamic properties, for example, volumetric heat capacity. Volumetric heat capacity is what? It is basically density multiplied by Cp. Cp is what? We studied that in thermodynamics. Specific heat at constant pressure. Okay? And its unit is joule per meter cube Kelvin. Suppose I give you in the exam, prove that its unit is joule per meter cube Kelvin. How will you prove that? I give you an exam, let's say 2 marks question. Prove that the unit of volumetric heat capacity is joule per meter cube Kelvin. Now do it. Yeah. Put the units and prove. So what will be the unit of density here? Unit of density will be units. Yeah, what's the unit of mass? Kilogram per meter cube. What will the unit of Cp? Joule per kg Kelvin. You forgot, huh? Joule per kg Kelvin. So if you substitute the values, you will get that it is joule per meter cube Kelvin. Done or not? Why is it taking so much time? Rho Cp. Rho is kg per meter cube. Cp is joule per kg Kelvin. Kg will cancel. That's it. Done. Okay. So volumetric heat capacity gives a measure of the ability of the material to store thermal energy. So you have a material, how much energy can be stored by the material itself is determined by volumetric heat capacity, okay, which is rho into Cp. The values of rho and Cp can be found in Appendix A. Appendix A is a table of properties, okay, which probably will be provided to you today. So I'm not going to go through the tables with you guys. Now you are already expert in reading the tables. So you read the tables yourself. Okay? So I'm not going to go through with the table. Yes, if you have any problem in reading the table, you can come to me and we can discuss your problem. But I'm not going to go through the tables with you. Okay. Thermal diffusivity. Thermal diffusivity is basically defined as alpha, and it is a ratio of thermal conductivity to the heat capacity. Okay. So in physical terms, if I am the material, okay, and the heat is being supplied to me, now I have an ability to transport the heat as well as I have the ability to store the heat. Okay. So it's a ratio of how much I will transport compared to how much I will store. A material which can store large amount of heat will not be able to transport much, because you will supply heat to it so that it can transport, but it has an ability to store much, so it will not transport, it will store. And the one which normally have less storage capability will then transport quickly, because their storage is full, then they transmit. So anyways, materials of large alpha. Now thermal diffusivity, it's meter square per second. I can give you an exam that kindly prove that the unit of alpha is meter square per second. Okay, you have the formula. Okay, K upon rho Cp. Substitute the values and you will get that its unit is meter square per second. Okay, so materials of large alpha will respond quickly to changes in their thermal environment, whereas materials of a small alpha will respond more sluggishly. They're taking longer time. So the material which has large alpha, large values of alpha, will quickly transport heat. Okay, or if you make any change in temperature at any point, it will be distributed very quickly. But the material with the small alpha will respond very slowly. So for example, wood has very small alpha. That's why if you heat it on one end, even you are holding it from the other end, you won't find any change in temperature. Okay. Is it clear so far whatever we have done? Okay. Now this first example, this is a very simple example and actually there is nothing much in it, but this example will help you go through the tables. Okay. And when you're going to go through the tables, you will find it a little difficult because first time you will have to spend some time understanding how the tables are written and how to take the values from them. They are not exactly the same kind of tables that we had in the thermodynamics, slightly different. So when I taught this course last time, students did not see the tables. Asked them, their first exam was pathetic because of that. Because in the exam, they thought that we will directly take values from the tables, and then when they saw the table, they did not know how to read the table. Okay, there are 3-4 things in it which are a little different, which when you go through the table, you will understand. But on the exam day, if you go through, it will be difficult. Okay, so this problem is nothing. This problem says take the values from the tables and just write it. But taking the values from the tables, it's most simple if you know how to read the table and everything. There's nothing much in it. The way units are written is a little complicated. You just have to, if you understand that, that will be easy. Okay. The thermal diffusivity is a controlling transport property for transient conduction using appropriate values of K, rho, and Cp. From Appendix A, calculate alpha for the following materials of the at the prescribed temperatures. So pure aluminium at 300 and 700 Kelvin, we need to find the values. Silicon carbide at 1000 Kelvin, paraffin at 300 Kelvin. Now the list where paraffin is given, I think that list is 2-3 page, and you have to at least search 15 minutes to find where is paraffin. Okay, that's why I'm saying you have to just go through the table once, and then it will be okay. But if you go through it on the exam day, it will not be that okay. Okay, so in this problem there is nothing. They say that you need to calculate alpha, but alpha has a formula K upon rho Cp, and take the values of K, rho, and Cp from Appendix A. That's it. Okay. For what material? For pure aluminium at 300 and 700 Kelvin, for silicon carbide at 1000 Kelvin, and for paraffin at 300 Kelvin. Okay. Yeah, 2 times. Okay. So when they found the values for pure aluminium, they found it for 300 Kelvin. These are the values. Okay. Just substitute into the formula, get the answer. Remember, thermal diffusivity alpha has unit meter square per second. What's the unit of acceleration? It's meter per second square. It is meter square per second. A little different. Okay. Anyways, but diffusivity normally have the same units. If you know kinematic viscosity, mu also have the same unit. This is thermal diffusivity, alpha. That was momentum diffusivity. Diffusivity has the same units, meters square per second. Okay. What's the unit of mu? Mu is viscosity, kinematic viscosity. It's right? Mu upon rho. If you substitute the values of mu, if you substitute the value of rho, you will get it's meter square per second. Alpha is also meter square per second. Then they find it for 700 Kelvin. Now there is interpolation, but there is one more thing important. If you see here, in order to find the values at 700 Kelvin for alpha, K upon rho Cp, okay, they found Cp for 700 Kelvin, they found K for 700 Kelvin by interpolation, but they used the value of rho for 300 Kelvin. Because it's not given at 700. And the main reason behind the theory behind is that for the case of liquid and gases, if you change the temperature, their density change is very significant. But this is solid. For the case of solid, change of temperature does not make significant change in the density. So if I have this pen and even if I heat it to 200 degrees centigrade, do you think its size will change drastically? Slight change. So the change in density is not that much significant for the case of solids. Okay. And also the value are not given. But this is not an excuse that the value is not given, that's why I'm going to take at 300. You need to have a logic behind. Why? And the logic is that this is solid. And for solids, change of density with temperature is negligible. Yeah, change of Cp with temperature is considerable. Also K will change with temperature. Okay, but change of rho is negligible. Okay, for the silicon carbide, again if you see here, rho taken at 300 and Cp and K taken at 1000, 1000.
If they're always like that, not change with any question.
If it is solid. If it is, it depends on what material you are saying. If it was liquid or if it was a gas, then you cannot take rho at different temperature. You have to then take the rho at the same temperature. Okay, that's why I told you once again. You need to go through the table. It's easy just to pick the value and write, but if you have not gone through the table, you don't know what value to pick and from where to pick. Okay. So that's alpha. Then paraffin. For paraffin, all the values were required at 300 Kelvin, that they were present at 300 Kelvin. But finding out paraffin itself is an issue. Where is paraffin? It's written that table A3. Go to table A3. It's a very big table. Okay.
Paraffin is two body atoms. Liquid?
Yeah, we don't know this one. That's liquid. It's liquid or solid.
Paraffin, yeah, normally it is actually solid. Okay, so, but it does not matter because the value are already provided there for 300 Kelvin and it was required for 300 Kelvin. Okay, so this problem was very simple. This problem was very simple. Nothing much to do, but this problem will help you go through the tables. Okay. Now this is a comparatively heavy problem. Okay. So let's move towards the second problem. This is a new problem? Formula is given in the problem actually. It says that use this formula.
Find the value of K.
Yeah. Okay. The bulk thermal, I told you what does bulk means? Large. Kathir, huh? Okay. The bulk thermal conductivity of a nanofluid. What is a nanofluid? You have any concept of a nanofluid?
Nano?
Nanofluid. Nano is very small. Very good, very good. The thing is that normally what happens is that you have the liquid carrying energy, okay? So most of the time it's like that, the liquid carry energy and then you make the liquid to move, okay? So for example, water, okay? If you want to carry a large amount of energy, maybe large amount of water is required. But sometimes what happens is that if you can dissolve or put some particles within the fluid, within the water, that particle has large thermal capacity, then the same amount of energy can, which was taken by that much big pipe of water, can be taken by a small pipe of water.
Okay,
then it is a nanofluid.
it's like bubbles.
It's not like bubbles, it's like particles, the sand particles, or yeah. So it's like water. Inside water, you have small particles.
Yeah.
So you put those small particles.
Heat it, so it become water.
No, you don't need to heat it. It's there. Just mix it. Now that water which was being carried by this much large size of pipe, the amount of energy which was carried by that much amount of water can be carried by a very small pipe with nanoparticles inside water, because the nanoparticles are those special particles which has very large thermal capacity. So it can carry a lot of energy in them.
Then how it's come water?
How it come?
Come water.
We don't need to put it in. We don't want to make it water. We want to make it the way it's a mixture of nanoparticles and water. Okay. It could be water. It could be some other fluid, but a mixture of liquid and solid. Okay. So these are known as nanofluids, and they actually reduces the size of system a lot. So if your system is using large amount of coolant water or something, okay, and you use nanofluid instead of water, simple water, then the size of the system drastically reduces. So maybe you make a very compact system, which is good. The world is now moving towards compact, small size systems. Okay, so that's the thing. So they say that the thermal conductivity of a nanofluid, which is uniformly dispersed, non-contacting spherical nanoparticles. Okay, why they are called nanofluid? Because those particles, their size is measured in nanometer. Nanometer is very small. You know, centimeter is 10 to the power minus 2, millimeter 10 to the power minus 3, micrometer 10 to the power minus 6, nanometer 10 to the power minus 9. Okay, so they are very small particles. Okay, so if we have that kind of fluid, now remember, in case of a nanofluid, if I have a nanofluid here, okay, so this is my nanofluid, but it will have a base fluid here, and within the base fluid I have particles. Okay, so these are particles. So nanofluid is basically a combination of base fluid plus particles, right? So we cannot use directly the property of base fluid, neither we can use directly the property of particle, because it is a mixture of two things. So if I want to know the thermal conductivity of nanofluid, it cannot be that of base fluid, it cannot be that of particle. But it is defined by this formula. This formula is what? If I want to know the thermal conductivity of nanofluid, so it use the thermal conductivity of the particle as well as thermal conductivity of the base fluid, as well as how many particles are there in the base fluid. Okay, so how many particles are there in the base fluid? This thing is defined by this phi. See, phi.
This is the number of the particles.
And this phi is basically known as volume fraction. Phi. Phi is the volume fraction, means volume of particle divided by volume of nanofluid. So if I have a total 100 kg nanofluid and particle 2 kg, so the phi will be 2 divided by 100. Okay, so it's volume fraction. Sorry, not kg, it's volume fraction, that means it should be in meter cube. So if I have 100 meter cube of nanofluid, then 2 meter cube of particles in it, so that means it's 2 upon 100. Okay, So it's volume fraction. Volume of particles divided by volume of nanofluid. Okay. So it's basically three terms here. Kp means thermal conductivity of the particles, Kbf, thermal conductivity of the base fluid, and phi, what is the ratio of particles within this nanofluid. Okay, where phi is the volume fraction of nanoparticles, Kb, Kp, and Knf are the thermal conductivities of base fluid, particle, and nanofluid respectively. Similarly, dynamic viscosity, mu Nf, is determined by this formula. Mu Bf for the base fluid plus 1.255, 1 plus 2.55. Determine the values of, now what do we need to determine? Determine the values of Knf. We need to find the K of Nf and rho Nf and Cp Nf and mu Nf and alpha Nf for a mixture of water and alumina nanoparticles. So your base fluid is what? Water. Your base fluid is water and particles are alumina. Okay. At a temperature of 300 Kelvin, so T is what? T is 300 Kelvin. Okay, and a particle volume fraction phi. Phi is 0.05, which is equals to Vp by Vnf, right? Volume of particle divided by volume of overall volume of the nanofluid. Okay. The thermophysical properties of particles are, for the particle alumina, the thermophysical properties are given. What is given? For alumina, the properties of particles are Kp is given, rho p is given, and Cpp is given. Specific heat at constant pressure of particle, rho of particle, Kp of particle, these three things are given. Okay, these you need to find. This is given, this is given. Is it clear? So temperature given, Knf you need to find, rho Nf you need to find, Cp Nf you need to find, mu Nf you need to find, alpha Nf you need to find, Kp is given, rho p is given, Cpp is given, and temperature is given, it is 300 Kelvin. Since the temperature is given 300 Kelvin and you know that what is your base fluid is water. So for water, the properties at 300 Kelvin you can get from the appendix, right? For water? Oh, yeah, we need all properties for water. Okay. So if we go there, okay. So from the table, okay, from the table it's written which table you will use. You will use table A6, but you need to go through the appendix to know which table you need to use. Anyways, by using table A6, the properties of water is, I will write here KBF, since water is my base fluid. So this property I will directly take from the table. Okay, KBF, rho BF, okay, CP BF, and mu BF. So these four properties I will take from the tables, appendix. Right? First of all, before starting solving the problem, do you understand the problem statement here?
Yeah.
You have a nanofluid. For the nanofluid, there are two formulas given. Formula for KNF given, mu NF given. And you are required to find all the properties for the nanofluid. For the particle, properties are given. For the base fluid, since the temperature was given, you took the properties from the table. That's it. Do you understand the problem statement? Okay. This problem is very important, especially this example 2.2, the one which we are solving, because in this book what they have done is that now in chapter number 3, in chapter number 5, in chapter number 7, 10, they have some problems regarding nanofluid, but they say that refer to example 2.2 for the properties of nanofluid. Okay, so the property of nanofluid, you will not find it in the table, but when you have to solve the problem in the future chapters and need to get the property of the nanofluid, they say refer to example 2.2, which is this example. So I can couple this example with any other example which is using the nanofluid in the future chapter. You get it? In the book they say go to take the properties from that example, but I will not give you an exam, go take the properties from that example. I will couple it. First solve example 2.2, then move ahead. Okay? Okay, now the first thing, let's start from K and F, because the formula is directly given. So we can directly start from K and F. If you see here in the formula for K and F, Kp, do we have Kp? K of particle.
Yeah, it's
Given, right? So Kp is there. Do we have Kbf? From the table, yes. Phi, given. Kp, given. Kbf, given. Kp, given. Kbf, given. Phi, given. Kp, Kbf, Kbf. Everything is known.
Yeah.
Just you need to plug in the values and you will get K and F. Okay? So K and F is done. Is it clear?
Yes.
Now the other formula is given for mu and F. So let's do this. For mu and F, what is required? Mu Bf.
Yeah.
Mu Bf
From the table.
from the table, okay? Phi, that's it,
Phi is given.
given. So everything is given.
Yeah.
So mu and F is also done. Is it clear?
Yeah.
Okay. Now the other things are a bit issue because they are not straightforward.
Nothing from the table, you have two programs.
Okay. Now let's move towards rho and F. In order to find rho and F, we have to apply the mass balance. Okay. What does mass balance means? Look, you have, let's say you have a mass, you have a nanofluid here. Okay. So the mass of nanofluid must be equal to the mass of base fluid plus mass of particle. Make sense or not?
Yeah.
Mass of nanofluid must be equal to mass of base fluid plus mass of particles, right? Now, tell me, is there any relationship between mass and density?
Yes. Volume.
Yeah. So density is equals to mass over volume, right? So mass, I can write it as density over volume, density into volume, right? So let's write it in that form. So MNF is rho NF, VNF, rho BF, VBF, rho P, VP, right? I can write this like this. Is okay? Now if I look into here, rho NF is something I need to find, right? Rho BF, rho B from table, right? So it's there. Rho P, given for particle, right? Okay. Now look, we know that phi is the volume fraction and it is Vp by VNF. Vp by VNF, right? So that means our Vp is equals to phi into VNF, right? Look from here. So our Vp is phi into VNF. So I can write instead of Vp. So now right now I'm replacing. Huh?
Yeah.
Okay, replacing Vp with phi VNF, right? Now tell me one thing, just common sense. If I say that in a fluid 5% is particle, then remaining 95% is what?
The other.
The other. Another is the base fluid,
Yeah, yeah.
right? So if Vp is phi VNF, then V base fluid is 1 minus phi VNF.
Yeah.
Make sense or not? If I say 5% is particle, then the 95% is the base fluid. Okay. So let me replace this VBF.
No.
Let me replace VBF with 1 minus phi VNF. Is it clear or not? So far it's clear, everybody. Is there anything which is not clear so far? Everything is okay, right? Now, if you see here, we have VNF here, VNF here, VNF here. Can I divide the whole equation by VNF? It will cancel, right? So VNF, VNF, VNF will cancel, right? Phi we know is given. So 1 minus phi here is also known. So what's left? So everything is known now, just rho NF. Rho NF.
So we find rho.
So we find rho NF, but by mass balance. I did the mass balance to find rho NF. There was no other way. No way other I can find. Is clear?
So, 1 minus this, is like equation?
Look, the thing is that if I say that phi NF, phi is 5%, so the remaining is the base fluid, total is 100%. So the remaining is 1 minus 5%, which is 1 minus phi. Okay.
So if I get the solution, then I can minus with 100.
Listen to him.
Can I minus 100 if like 50%? The answer. Can I minus with 100? I get the
No, don't do that. Don't do it like this. Don't do it like that. I didn't know what he said, but anyways. Okay. Okay.
minus.
Okay. You understand it or not?
Taking the value just from one, just one, put it 100 and 29 like this.
Okay.
But even just understand it.
Okay. So I find rho NF. Okay. So now let's try to find CPNF. For finding CPNF, for last time we did the mass balance. Now we need to do the energy balance. Okay. So energy balance. If you understand the mass balance, energy balance will become easy for you. Okay. Energy balance is the same thing. So that means energy of the nanofluid is equals to energy of the base fluid plus energy of the particle, right? And you know that for the case of energy, we can write energy is mCpt. mCp delta T, this is thermodynamics. Chapter number, I don't know, 4, I think. Right? mCp delta T. So, since in this case, the temperature is not changing, it's the same temperature, 300 Kelvin for the nanofluid or for the base particle or for the base fluid or for the particle. So T is just T, okay, it's not changing. So let me write it like this. So it will be M nanofluid Cp nanofluid T is equals to M base fluid Cp base fluid T plus M particle Cp particle T, right? And since T is common, it's the same, I can cancel T, okay? Okay, also mass, like the way we replaced mass with density, I can replace it like here as well, okay? So now I'm going to do it directly, okay, in one step. So here I'll put here as rho NF VNF, rho NF VNF, right? And here I'll put it as rho BF 1 minus phi VNF. I did exactly the same thing. I just wrote the same thing here, okay? So MBF, we did this thing. So MP, exactly I will write this thing. So rho P phi VNF, right? Now VNF can cancel here as well. Okay. I know all the densities now.
Yeah, yeah.
Density is known, density is known, density is known. Let's talk about CP. CPNF I need to find. Okay. CPBF
Okay.
from the appendix and CPP given. Is it clear? So by energy balance, I have found what is the CPNF. Is it clear? Since you studied, you understood the mass balance, then I just directly in one step put everything from there to there. I just needed to replace masses with these things.
We need to know the steps.
Yeah.
From where we start. Okay. If we start directly to the CP and we don't have the
No, if you directly move to CP, then you cannot.
don't have the density.
Yeah, then you cannot. You should do density first, then you can do CP. Is it clear or not? Okay. Alpha, because you have all other things for NF already available, so you can find alpha, because alpha is equals to K rho CP. Now you have K for NF already in the very first step you did using the formula there. Rho you determined by mass balance, CP by energy balance. For N, for nanofluid, all other things are available, so that's why finding alpha is not an issue. I gave this question last time in the exam, the very first exam.
Very fast.
The first exam, first exam. I gave this question and I modified it. What modification I made? The modification.
We don't know to know. We don't want to know.
Okay. Okay.
We will know that.
Okay. Is it clear? Is there anything that you do not understand in the solution of the problem? The problem was a bit complicated, yes, but it could be done. It's
So the next chapter, we need to do all these steps to get this value, to use it in the second part of the question. Wow.
questions are big.
Oh, that's very big. There is difference between thermo and
The heat is more hard.
it is more deep.
So this all thing is done exactly the way. They, in the book they do it directly. I mean, I write here that we did the mass balance. They do not write here that they are doing mass balance. They just directly put everything. So
Thermo was unbelievable.
okay, khalas. So you understand everything in it? Is there anything that you don't understand? Please don't mess up in units. This is one very major thing in this course, because units are so many coming and it becomes confusing. Okay, and students don't write units, and what happens is that then they confuse in the values. So don't mess up in the units. Okay, even when you are going through the problem of your lecture, just try to focus what were the unit used, why they use these units, so that you don't get confused any place. Okay. Okay, let's move towards the next topic. Do you need a break? Okay, anyways, let's start and continue with what we were doing. Okay, so now let's develop the main heat diffusion equation. This is a small derivation, but this is a kind of a derivation that can come directly in exam. Okay, so now we are going to develop the heat diffusion equation. It's a differential form of equation. These equations are developed in three different type of coordinate systems. One is the rectangular coordinate system, where you know it's x, y, and z. Then we have another coordinate system, cylindrical coordinate system, In the cylindrical coordinate system, it's not x, y, and z. It's along the radius, along the circumference. So it's r, theta, z. Okay. Then we have the spherical coordinates, and in spherical coordinates is like on a ball. So you have one angle 360 degree in one direction, then 360 degree in the other direction. So you have two different angles, and then you have the radius. Okay. So anyways, the heat diffusion equation is in the book. It's derived for all the three coordinate systems, but we will derive it only for one coordinate system, which is the rectangular coordinate system. However, the results for all the three coordinate systems we are going to use in the next chapter. Okay. So the final result for this heat diffusion equation will be provided in the book of formulas, and it is there in the book of formulas. So let's derive the main heat diffusion equation. Okay. So the derivation of main heat diffusion equation starts with what we do is that we take a differential element, we take a small element. Okay, so let's say we take a small cubical element. Okay, this is my small cubical element. I want to keep the coordinates same. So just to, I have also done this a handwritten derivation. This is a handwritten derivation that is done here. Okay, so we have this is our x-axis, okay, and this is our y-axis, and this is our z-axis, right? This is our small element. Now, in the small element, what we assume is that heat is passing through it in all direction. Heat is passing through it in all direction. So we have heat passing through in the x direction, then we have heat passing through in the y direction, then we have the heat passing through in the z direction. Okay, so since this is a small element, small cubical element we are considering, so this is the x direction, so let's say that this length is dx, and this is the y direction, so let's say this length is dy. Okay, and this is the z direction, so let's say this length is dz. Okay, so our volume is basically dv, small differential volume, which is dx into dy into dz. Okay, now what we assume is that heat is passing through the cube in all directions. Okay, so we have a heat which is entering from this face, and we can call it as qx. It's a heat entering in the x direction. So if the heat is entering in the x direction from this face, then the heat will be leaving from this face, okay, and it will be qx plus dx, okay, after a distance dx. Okay. Similarly, we have heat, the vertical direction is the z direction. So we have the heat entering in the vertical direction, it's qz, and after passing a distance dz, so it's going to come out as qz plus dz, okay, after a distance dz. Similarly, in this direction, heat is entering in y direction, so it's entering as qy, and at the back it will be leaving, and at the back when it leaves, so it leaves as qy plus dy, right? And we also suppose that within this, we also assume that within this small volume, we have some heat generation element inside. It could be anything. It could be some combustion going on, some heater, electrical heater there, whatever. So there is something which is producing heat inside. Okay, so there is QE generation, energy generation inside this box. Okay, and normally any energy generation is a factor of volume. Okay, so So we assume that this energy generation is given in the specific volume term. So it's energy generated per unit volume, is basically. Okay. So the total. Okay. Now let's apply the first law of thermodynamics. What is the first law of thermodynamics? If a total energy in equals to total energy in minus total energy out plus total energy generated is equals to total energy stored. Is a general terminology for first law of thermodynamics. E in minus E out plus E generated is equals to E stored. Right? So if E in is equals to E out and there is nothing generation, then nothing is stored. Right? So that's the first law of thermodynamics. So let's talk about this. If we have the first, based on the first law of thermodynamics, what is our E in here? Qx plus Qy plus Qz. Okay, oh, Qx plus Qy plus Qz, right? What about E out? Qx plus dx plus Qy plus dy plus Qz plus dz, right? These are our E in, this is our E out. What about Eg? E generated. If let's say that Q is the amount of energy generated per unit volume, then we have Q multiplied by the volume. That's the total energy generated, right? So multiply by the total volume is dx, dy, dz, assuming that this is per unit volume. Okay. So we have E generated. What about E stored? E stored will be, we can determine it as m dot Cp delta T, m dot Cp delta T. Energy stored will be in the term, if there is energy stored, there will be change in temperature. If there is no energy stored, no change in temperature. So change in temperature will correspond to the energy stored based upon what is the capacity of this thing. Multiply by m dot. Okay, m dot is mass per unit time, mass flow per unit time. Or so if we can say that's m upon dou T, or let me put dou T from here to there. So change in temperature with time. Okay, so that's the energy stored. So we have energy stored, energy in, energy out, Eg, energy generated. We can substitute all these values in this main equation, right? Now there is one thing, Qx. Qx is heat flow, because this we are considering for the case of conduction, right? This is all the heat diffusion equation, for conduction equation. Okay, so for conduction, Q is given the value by Fourier's law. So as per the Fourier's law, Q is equals to negative K A dt by dx, right? So that is okay. Anyways, just this was the main equation. Yeah, this was the main equation. This is the E in, this is E out, this is E generated, this is E stored. Okay. Okay. E stored we can also modify it further because this is mass. So mass we can write in terms of the density. So that will be rho volume, but volume in this case will be dV. That's the volume that we have, and I can replace dV with dx, dy, dz, Cp dou T by dou T. Okay. So this is what is done here. E stored. Okay. Now, by the Fourier's law, we have Q is equals to negative K dt by dx, right? So if it is Qx, okay, then it is negative A negative K A. A is the area across which it is flowing. So in this case, area is what? dz multiplied by dy, right? So in this case, it is dy dz, right? So for the case of qy, it will be dx and dz, okay? And similarly for the case of qz, it's dy dx, okay? And for qx it is dt dou t by dou x, for qy it will be dou t by dou z, for qz it will be dou t by dou z, because this dx dy dz is the distance across which heat is being flowing. Okay, so if it is flowing in x direction, it flows a distance of dx. If it is flowing in y direction, then it flows a distance of dy. If it's flowing in z direction, it flows a distance of dz. Is it clear? So we have now qx, qy, qz. Okay, so we have qx, qy, qz. We can substitute these values here. Okay. And now we have this E out. E out is qx plus dx, qy plus dy, qz plus dz. You have you taken the course of linear algebra?
Yes.
So you know about the Fourier expansion? You must have gone through Fourier expansion. If you have this kind of a thing, qx plus dx, how do we expand it in the Fourier series? Have you studied Fourier series? Have you studied series?
Do you mean multiply it by a number, both sides?
Have you studied series, Taylor series? Have you studied Fourier series?
Maybe we take it.
No, I don't know.
Okay.
Try to ask, but maybe we will.
Anyways, this is Fourier expansion. We can write a term qx plus dx in Fourier expansion, and in terms of Fourier expansion, it is qx plus dou qx upon dou x dx, and then plus many terms. However, since we know that dx itself is a very small, this is a very small unit, and dx is a very small length, so the next terms will be having dx squared, then dx cubed, and dx to the power 4. So if your value is very small, then power will become much small. Almost something can be neglected.
Yeah.
Okay, so we can neglect the other terms. So we just keep the two terms here. So this is the expansion. Okay, so we can expand qx plus dx as qx plus dou qx upon dou x dx. Similarly, qy plus dy can be expanded as qy plus dou qy upon dou y dy. Similarly for qx plus dx. Okay, so this expansion is known as Fourier expansion, Fourier series expansion, and maybe in future some course if you will learn it, if you have not learned it so far. Anyways, it should be a part of linear algebra. So this is the expansion, E out. It's written here. Okay. Now we have E out value, we have E in value, we have EG value, we have E stored value. Everything you put into the main equation. It becomes very long equation, right? It becomes very long equation, and once it becomes a very long equation, divide everything by dV. Because each equation has volume value, e.g. it has volume term, E stored it has a volume term. Okay, others it has dx, dy, dz, it will be there. So divide everything by dV, the whole equation divided by dV. In the end, it will come up to be this thing. That is the final form of the equation. So you will have Q dot, remember it was what? It was energy generated per unit volume. That was per unit volume term, this, okay, plus dou by dou x k dt by dx. This is the main equation important for the next 3 chapters. This is the main equation for the next 3 chapters. Chapter number 3, 4, and 5. Okay. So Q dot, that's energy generation per unit volume, plus dava by dava x, K dava T by
3x
dava x,
plus
plus dava by dava y,
the same
K dava T by dava y,
plus z
plus dava by dava z, K dava T by dava z equals to rho Cp dava T by dava time. Okay, this becomes the main or fundamental equation for heat diffusion in Cartesian coordinates x, y, z. Okay, now you need to understand each and every term in it. The first term is about the heat generation. If there is no heat generation, then this term will be 0.
yeah, okay.
This term, okay, you see here K is inside these brackets. So that means K could be dependent upon direction. But if K is independent, if the material is isotropic, K will become out.
Same on the all the
K will become out.
okay.
Because K then it's not doesn't depend upon X, Y, or Z. So K will come out if it is isotropic. Okay. Okay, this is for 3 dimensions, heat transfer in 3 dimensions, in X, Y, Z. If it is a one-dimensional problem,
Depends on the direction.
yeah, suppose it's one-dimensional problem in X direction.
So we neglect y.
Y and Z is not there. If it is 2-dimensional problem in X and Y,
So z is not.
Z is neglected. Okay, this is the term which shows that change in temperature with time. Okay, so anything that changes with time, that means it is unsteady.
Unsteady, yeah.
Okay, so if it is unsteady, then this term will be there. But if it is a steady state, this term will go 0. Okay, so unsteady is also known as transient. So I can bring this equation and I can ask you to simplify it for an isotropic problem with no heat generation for 2-dimensional flow and unsteady state.
The same this question in thermo, I remember, right?
Yeah, similar it was. You understand that? You should understand all these terms here. And what does it mean and how, if I say it is isotropic material, then what will happen if I say that it is non-isotropic, then what will happen?
So, Dr. CB, and okay, if this term is unsteady, so the whole term is 0. Okay.
Because dava T by dava del dt, it becomes 0. There is no change with time. Is clear? If it is isotropic material, then K will come out. So this K will come here, this K will come here, this K will come here, and then it can become square because dava by dava x into dava T by dava x, so it becomes dava square T by dava x square. Right? Is it clear? Then we can do it like this, or we can. What we can do is that if we want, we can divide the whole term by K, whole equation by K. Then it becomes Q over K. The K will be removed from here. K will be removed from here. K will be removed, and this becomes also K here. And but rho Cp upon K is what?
1 over 8.
1 over alpha.
Alpha, sorry.
Okay, so becomes 1 upon alpha. Okay, so now it is an isotropic problem case. Anyways, this was the main formula for the heat diffusion equation. Okay, this is the major formula which is going to be used now in chapter number 3 a lot, and from this onward you will have very long derivations, all differential type derivations. Okay, numerical problem, differential type, but no values you will use, just dava for 3 pages. So it's like that. So and this will become the basis for chapter number 4 as well. This will become the basis for chapter number 5 as well. Okay, so chapter number 3, 4, 5, this equation becomes the basis. Yeah, now remember, this is the derivation that we have done for the Cartesian coordinates. I can ask you directly to derive this equation in all the steps that we did here. Okay, so this can come as a full question. If it comes, it will come as a full question. Proof. But as a full question, I mean 10 marks, not 2 or 3 marks. Because this is a long proof. Okay. Now, as I told you that a similar kind of derivation is present for the cylindrical as well as the spherical coordinates, but it is there in your textbook and we have not gone through it. Okay. However, the answer is important and understanding the answer is important. If you see here, answer, okay. So we have change in temperature because in cylindrical coordinates, instead of x, y, and z, you have r, theta, and z. Okay, so you have derivation a term with r, change in temperature with theta, change in temperature with z. Then you have the q generation term. Okay, and then you have the unsteady state term. So I can ask you to, instead of giving you the main equation in the Cartesian coordinate, I can give this equation and ask you to simplify it for 2-dimensional, unsteady, and like that. Okay, but the terms are similar. So here, instead of x, y, z, we have r, theta, z, and this is with respect to time, and this is the q generation term. Then we have in the spherical coordinates, it's like this. In the spherical coordinates, we don't have r, theta, z, we have r, theta, phi, because we have two angles. One angle for 360 degree in this direction, one in the other direction. So we have r, phi, theta. Okay, and then you have the generation term, and then you have the unsteady term. It's like that. K's, you can see K's inside, but if it is isotropic, you can keep the K out. Okay. So anyways, these formulas are also present in the book of formulas. I prefer that you go through the book of formula regularly so that you try to remember that where these formulas are. In the end, you will have so many things and it will take a lot of time for you to find out where these things were present. Okay. Okay, so now we move towards a numerical problem related to this heat diffusion equation. This is Introduction to Conduction, this chapter.
Until now it's okay though.
The problem with this course is that when you're going to take it with me, at any step, inshallah, it will be okay. But there will be so many okays accumulated in the end that you will get hugely burdened. So at any specific step, it will be okay. But in the end, you will have 1,000 okays with you.
So I have to guess.
Okay. So far is done. So far, no issue. No. There is nothing which is not understandable. What is the time right now? 2:20. 10 minutes, inshallah, we'll finish this problem in 10 minutes. Okay, we have a temperature distribution across a wall 1 meter thick. So you have a wall and its thickness is 1 meter. So that's the wall, suppose, and it has 1 meter thickness. Okay. At a certain instant of time is given, so that's the temperature distribution. So suppose you say that this end is x, this end is x. So the temperature distribution within the wall is T is equals to A plus B x plus C x square, right? So if you know any position of x, you can find what is the temperature. A, B, and C are known. Okay. So where T is in degrees Celsius and x is in meter, while A is 900 degrees centigrade, B is negative 300 degrees centigrade per meter, and C is negative 50 degrees centigrade per meter square. Why they put it centigrade per meter square, centigrade per meter, degree centigrade? It corresponds to the equation. Because temperature should be in centigrade, then the unit of A should be centigrade, and unit of B should be centigrade per meter, so that meter will cancel. Unit of C should be centigrade per meter square, so that meter square and meter square will cancel. Okay. Anyways, A, B, C value is known, so if you know x, you can exactly know what is the temperature at that point. Okay. A uniform heat generation, there is a uniform heat generation, so there is heat generation in it, and it is 1000 watt per meter cube. Okay, so that's Q dot, inside is 1000 watt per meter cube. Okay, is present in the wall of area 10 meter square. So this wall, the cross section is 10 meter square. Okay, so this area is 10 meter square. Okay,
This is the cross section, no?
this is a cross section,
Why?
but the thickness is 1 meter.
Okay.
Thickness is 1 meter, and cross section, suppose this is x axis, then y and z axis is completely 10 meter square. Okay. Now the properties of the wall are given. Properties of the wall is that density is 1600 kg per meter cube. So density of the wall is given, and K is given for the wall, and Cp is given for the wall. Okay. Determine the rate of heat transfer entering the wall. Now, as I tell you, always be focused over the units. So sometimes the units are played very tricky, in a very tricky way. For example, if you see here, value of Cp is 4 kilojoule. When you will be solving everything in what kilo should come as 1000. Okay. So if you directly use the value with 4, then something will go wrong. Okay. So always try to focus over the units. Determine the rate of heat transfer entering the wall and leaving the wall. So we need to find out what is the rate of heat transfer entering the wall, what is Q in, and we need to find out what is Q out, leaving the wall. It's written, entering the wall means x equals to 0,
Yeah.
means here, the beginning. Leaving the wall means x equals to 1 meter at the end. Okay, so Q in. Let's first talk about Q in. So Q in, basically it will be what? We know that Q is equals to negative K A dou T by dou X, right? It's like this. We know T as a function of X. Can we find what is dt by dx?
Yes.
What?
It will be the B plus CX.
Divided by x.
B plus
C.
C, 2cx, right? B you know, C you know, and when we want to find it at the entry point, what is x? 0.
So the term is 0.
So that this term will be 0, so dt by dx is just B. Okay, so you know what is dt by dx because B and C and A are given. Okay, so you know what is this? Area is already given, 10 meters square.
Case.
Okay, K is given.
The area, which area? It is that for the, so that one.
Yes, but it is given 10 meters square. Okay, so we have Q in comes out to be okay. So this dt dou t by dou x will be actually it will be B. Okay, so BKA. Okay, that's it. With the negative sign means it is entering. It doesn't matter even if you don't put in the negative sign. No problem. Is it clear? So that's Q in. Q out. Same, negative K A dou T by dou x. So this was at x equals to 0, but this is at x equals to 1. Okay, so now you will have x, so it's actually B plus 2C. Now it's like this. Okay, so just substitute the values and Q out. So you got it. Okay, so first part is done. Determine the heat transfer entering and leaving the wall. Okay, now determine the rate of change of energy storage in the wall. Now we need to determine the rate of change of energy storage in the wall. For that we need to apply the first law of thermodynamics, the way we applied in the heat diffusion. Okay, so we have E in minus E out plus E generated is equals to E stored. It's like this. Now E in we know, that's Q in. E out we also know. E generated, it's given 1000 watt per meter cube. Remember, we found E in as watt, E out as watt. It should also come as watt. So but it is given as watt per meter cube. So we need to multiply it with the volume. Volume multiplication is very easy because area is given and the thickness is given. So you can get the volume easily, right? So E generated will be what? E generated will be Q multiplied by area multiplied by this length L, thickness. Is clear? And everything is given. So you get this. Khalas, this is the energy stored. This is energy stored. Determine rate of change of energy storage in the wall. You got that. Now determine the time rate of temperature change at x equals to 0, x equals to 0.25 and x equals to 0.5. Now since we need to find the time rate of temperature change at these points, okay, so we need to move back to our heat diffusion equation. What was our main heat diffusion equation? Okay, our main heat diffusion equation was Q dot plus dou y square T by dou x square plus dou y square T by dou y square plus dou square T by dou z square is equals to rho Cp dou T by dou T. Okay. Oh, I forgot K here. So K here, K here, K here. That's it?
No, K there. No.
Okay. This was our main heat diffusion. This is a one-dimensional problem, right? Heat is only transferring in one direction. This is a one-dimensional problem, so I can cancel this. Heat generation is there, and we need to find time rate of temperature change. Time rate of temperature change is this thing, right? This is what we need to find. Time rate of temperature change. So if we want to find this thing, okay, Q dot is known, no problem in it. Q dot is known. This is exactly what we want. K is also known. Dou y square T by dou x square. Can we find it? So we know dt by dx is this thing. So what will be d square T by dx square? 2c. Got it? So now we also know this thing. Is clear? We know rho, we know Cp. We can find dou T by dou T, dou temperature by dou time. Okay, that's the time rate of temperature change.
Just the time. You can substitute the value into the.
So we need to find the time rate of temperature change at x equals to 0, at x equals to 0.25, at x equals to 0.5. Now the thing is that if dou y square T by dou x square was a function of x, then you use the value of x0. But here in this case, it will be same value because nothing is function of x here. Is it clear? So we have this for the second part done, and this. So that's it. So we found Dawati by Dawati. Okay, and how did we find Dawati by Dawati? Directly substituting all the values. Is it clear?
Doctor, number 2, doctor. From where did we bring it? E.g., the energy storage.
The energy storage is energy generated.
And
Energy generated is 1000 watt per meter cube.
okay.
So you have to multiply it with meter cube. The volume. Where is the volume? Volume is area multiplied by the thickness. Thickness is L. Area is A. Is it clear?
Yeah.
Okay. So in this way, your this problem is also done. Just a minute. Okay. Okay, خلاص. This problem is also done. Now there are 3 different kind of boundary conditions. There is no problem. It's just a theoretical thing, but I brought this in the final exam. Short question, 2 mark. Write down the 3 kind of boundary conditions. On chapter 2. So they had to write what are the 3 kind of boundary conditions. So we have 3 different types of boundary conditions. One boundary condition is known as Dirichlet condition. The Dirichlet type of boundary condition is that if you want to solve for the temperature within the complete body, if at any one point temperature is known, then that kind of boundary condition is known as Dirichlet boundary condition. In Richlit boundary condition, look, the thing is that we have this kind of equation. In order to solve, you have taken the calculus and 1, 2 and differential equations. In order to solve these kind of problems, you need boundary conditions. Without boundary condition, you cannot solve a differential equation, 2 degree, 3 degree differential equations. You need boundary conditions, okay? So what kind of boundary condition is provided to you? If the boundary condition is such that at any point or at any surface temperature is known, okay, then that kind of boundary condition is known as Dirichlet condition. If at any surface instead of temperature, what is known is the heat flux is known, okay, then that kind of boundary condition is known as Newman condition, okay. And there is a third kind of boundary condition in which neither the heat flux is known nor the temperature of the surface is known, but what is known is that amount of heat conducted is equals to amount of heat convected. The amount of heat conducted at the surface is equals to the amount of heat convected out of the surface.
Okay.
If this is kind of the condition which is known, then this is the third kind of boundary condition. We call it, we don't have any name for it, we just call it boundary condition of third kind. So what are the 3 kind of boundary conditions? Either at any boundary directly temperature is known,
No.
or temperature is not known,
But the actual
heat flux is known, or neither the heat flux known or the temperature is known, but what is known is that the amount of heat conducted at that surface equals to amount of heat convected out. If this is the condition, then this is known as the third kind of boundary condition, okay, boundary condition of third kind. So they were given in the final exam a short question for 2 marks. Write down the name of the boundary condition and just explain. So they had to just write Dirichlet condition, Newman condition, boundary condition of third kind. In the bracket they have to just write Dirichlet means temperature known, Newman means heat rate, heat flux known, and third condition boundary means amount of heat conducted equals to convected. But since it was given, since this has been given, so it means not going to be repeated.
No, you might say not repeated and we will see.
Yeah, of course.
So don't say anything.
Okay.
Just study it.
Just to study it, yes. This is an example 2.4, but it's not literally an example. It's just showing the different kind of conditions here. You can go through it yourself. It's not something which can come in exam. Okay. So with this, our chapter number 2 is over.